today we're going to talk about coupling agents, which is chemicals that we're going to use to attach a surface to something else. So it will be a binder between a paint, for example, and a material, or between two materials through glue. The simplest one from an organic chemistry perspective is probably the soap molecule. So let's draw one of those and a metal surface. So this is our soap molecule, dodecyanoic acid. It's got 12 carbons, C double bond O, single bond OH. So that's our normal soap. And as you will know from home and from living here perhaps, if you mix soap with normal water, very often a hard, scummy material drops out and it sticks to the bath and it sticks to the sink. Some of you will live in very soft water areas where this doesn't happen. This material is the salt of this soap. So a metal ion comes along and is attracted to this center, which has got two negatively charged oxygen atoms. The negative charge is distributed between them both. So they've got about half a negative charge each and half a double bond, so 1.5 bonds each. And the metal ion, it's got 2+, comes and sits in the middle. If it collects two of these, it becomes highly hydrophobic, so it doesn't dissolve in water anymore, and that's the soap scum. Typically stearate, which is 16 carbons, and calcium. But what happens if we have an iron atom at the surface of our material? Sorry, let's try that again. What happens if we have an iron atom at the surface of our material? Then it can do exactly the same thing, but then it's attached to our surface, which is the whole point of this subject. So now what we've done is we've attached it to this iron atom. It's now the equivalent of a complex, but half of the complex is stuck to our surface and the other half is now projecting into the solution. And now we've generated a connection between our metal and some organic material. So if we were now wanting to put something organic on the surface, it would interact with this long chain much better than it would with the iron oxide surface. So here's a complex, just to remind you. We've got a metal ion, in this case it's iron, 3+, and it's surrounded by negative ligands. These are, in this case, chloride ions. So we've got 4 of those. That makes it in total 1 negative charge. That's the minus over there. And we've got 2 waters on it. That would be a fairly standard state for a metal to be in water. And if we have our metal attached to a surface, we can imagine that only some of them are covered. If we want to attach something better, so stronger, than these chloride ions, we can occupy more than one of these positions. There are 6 of them in this case. It's an octahedral complex, so that it has 6 possible positions, and if we occupy 2 of them, which is what the acid does, that would be a standard chelating agent. If it's better, it might be able to take up more, so some of them have more ends and can attach to more of them. The very common EDTA, ethylene diamine tetraacetate, has 6 possible positions, so it can occupy all of them. It wraps around the whole ion, or the whole metal ion, and hides it from the solution. EDTA is used in blood bags when you give blood to prevent the blood from clotting, which it does by pulling calcium out of solution and making the effective concentration very low, because the calcium doesn't do the thing it's supposed to do, interact with other molecules, because it's too busy interacting with the EDTA, which sticks to it very, very well. An alternative would be a phosphate like this, where the phosphorus can bind also via oxygen to our metal ion. In both cases, what we would expect is that the complex that we form is completely insoluble, so even if we didn't have this organic piece on there, our iron oxide would be pretty insoluble. If we didn't have this on here, our metal phosphate would also be typically insoluble. Going away from oxygen, we can think of alternatives. So this would be Benzodiazole, which is a corrosion inhibitor for copper. It's used in central heating and that kind of thing. And if we add molecules, if we add groups to this side, we can make it attach to the thing that we want. In this case, it's not very attractive, but it binds to a copper surface. Corrosion inhibitors and coupling agents are very similar in many ways. This here is a thiol, which is the sulfur analogue of an alcohol, and what that does is it tends to bind to gold and silver and sometimes to copper. So now we can ask ourselves the question, why does this bind particularly to gold and silver and to iron 2, and the carboxylic acid binds particularly well to iron 3? And why does this nitrogen compound bind particularly well to copper? So I had a bit of trouble with my pen. Let's first of all consider this. The size of the orbital matters. So in this case we are trying to donate electrons from a lone pair to our metal. That's the ligand transfer mechanism. So we're giving it electron density from our ligand, and the electrons that come from the ligand are going to come from some kind of orbital. The oxygen orbital is one period smaller, so it's one shell smaller than the sulfur orbital, and that means it's way smaller. That's good and bad, because if the metal has a similarly sized orbital, remember this is going to be the d orbital typically, one of these orbitals, one of this kind of d orbitals that's sticking out of the metal center, and that's going to interact with here. Actually it will be a hybridized orbital, so it won't be quite the same geometry, but we'll stick with that to start with. The sulfur, on the other hand, can't interact very well with narrow orbital like that, and so it gets worse orbital overlap, which means that the bond is weaker. So our sulfur ligand can attach very strongly to larger metals, lower down in the periodic table, and our oxygen ligand attaches very strongly to small metals high up in the periodic table. But that's not the only thing, because I also mentioned that iron 3 cares whether it's oxygen or sulfur, and iron 3 tends to stick to oxygen ligands, iron 2 to sulfur, because the higher the charge on the metal, the tighter the control of the electrons is, and so the smaller the effective size of the orbitals. So there again we have the same effect to a certain extent. This is an important effect. It comes from organic chemistry as well, that things with a large orbital on them will tend to interact better with a reaction partner that has a large empty orbital to react with, and things that have a small one will react better with those that have a small empty orbital to react with. Also, if we look at these molecules, we can imagine that the distance between the two electron pairs effectively is going to be slightly different, and that will obviously fit better with some metals than with others. And this molecule here, for example, that attaches to copper particularly well, is going to be slightly different again, because it's donating out of p orbitals out of the side of this molecule, and it will also have slightly different angles and slightly different directions, which will determine the size of the metal atom and maybe the crystal structure that it is going to bind to best. At first glance, the thiol doesn't look very much like the acid, but the reaction with the surface is very similar. The hydrogen on it drops off as a proton, giving 2 electrons to the sulfur, which can then attack a gold atom. That forms a kind of bond. It's not a full bond, but it's nearly a full bond. It's very strong. Likewise, if we take a calcium atom and we do this approach a carboxylic acid, the same thing can happen. A proton falls off, the 2 electrons go into the oxygen and either join the calcium directly or form a double bond and kick the other double bond out to bind to the calcium. In that case we end up with 2 half bonds, and the same thing pretty much happens. There are a whole family of thiols of similar compounds that we will not consider right now. There are a whole family of thiol-related compounds with similar reactions that we won't go into right now, because we want to get to the other type of coupling agent which reacted with a different molecule. If we take a generic metal ether, it's got some kind of groups on it, but it's got this metal ether bond. It's got MO and organic. That would be a metal ether, and it doesn't behave exactly the same as normal ethers. Normal carbon ethers are fairly stable. They're quite difficult to break. Metal ethers are not so difficult to break. Water can come along and hydrolyze them. So the lone pair of water can come along, it can join an empty orbital of the metal, and that can kick out the alcohol, or what will become the alcohol once this proton has transferred to that anion. Depending on what the metal is and what the side group is on the ether, the reactivity will vary. The ones used in coupling compounds are typically titanium, sometimes zirconium, and silicon. Silicon is by far the most common. An alternative would be to have a chloride on there, and this will involve SN2 substitution of the chloride from an OH group or from an oxygen on the surface. You can imagine that silicon and also titanium are particularly good at reacting with oxygen to form silicon dioxide or titanium dioxide, but it can't get rid of these organic groups quite so easily. It can get rid of this chloride. So here we have a hydroxide bond in the surface of our material, and it's going to attack with a lone pair to the silicon, causing the chloride ion to leave. The hydrogen ion will have to leave either before or afterwards, and that will form in the end the other product, which is hydrochloric acid. The ethers, the silyl ethers, behave slightly differently in that they usually hydrolyze to form silicic acid beforehand, and that then reacts with the surface. Titanates tend not to do this. They react directly, just like the chloride does, and lose their side group. They're more reactive than silanes. Silanes are more useful if we want to store the product, paint for example, for a bit longer, because the silyl ethers are more stable in solution. Silyl chlorides are not very stable. They're very reactive too and tend to stick to things. So our surface is still going to provide electrons, and in the end we're going to lose water in this case. Depending on whether we leave one or multiple groups on our silane free, we can either connect it to one bond straight to the surface, which effectively titrates the surface bonds. We're only attaching to things that are already there. Or we can form a network, which has the drawback that it tends to form a thicker layer. Has the advantage that if there's some kind of area here that isn't reacted, we can bridge over it. This is often necessary on polymers that we've activated with a plasma or with a corona discharge, and then we need to have a coating on the top. We can start it going with this, and now we have our chosen group on the outside. For a metal, it's less important because metals tend to have metal oxides, hydroxides on the surface, and then we will have a lot of groups that we can attach to, although sometimes it's used on metals too. The important part is that we can choose what this reactive group is or unreactive group is, and so we can determine the chemistry of our surface now to be what we want. Some of the more common coupling agents would be simple chain molecules to make it hydrophobic, which would be a way of getting things to dissolve into, suspend into organic solutions, which normally wouldn't, such as polymers, for example, and such as metal particles, which will then dissolve in organic solutions or suspend in them better. So if we want to make some paint, for example, we may have to treat our color particles, our inorganic color particles, with a silane that's got a long chain on it. For other purposes, if we want to have an additive to polymers, a filler material or anything, then we might also do the same thing. We don't want it to bind to the polymer necessarily, because that will change its flow characteristics, and so that would be bad. But we would like it to mix very well and disperse in the polymer, and so we would like its surface to behave like polymer. If we're going to disperse it in polyethylene, this would obviously be a very good choice. We might also have a double bond if we want to do an attachment reaction. So if we're going to cover this with a reaction mixture that's going to form polymer by free radical initiation, this would be a fine way to start, because then it will be involved in the reaction and will actually link chemically all the way through to the surface. That isn't always a good idea, but if we want to do it, that could be how we would do it. Another very common variation is the amide group. Because of its reactivity, we can connect it to proteins, for example, but we can also connect it to epoxy adhesives, which is many types of paint and adhesive. We can look at that reaction. Here is an epoxy. It's a 3-membered ring with an oxygen in it, and we have our nitrogen here, which is going to donate its lone pair into the anti-bonding orbital of this carbon-oxygen bond. That kicks it out, and there will be a proton transfer. Let's just fix the reaction here. That forms a bond between the nitrogen and the first carbon. The oxygen ends up on the second one, and the rest of our polymer carries on from there. This was bonded in here, and the hydrogen comes from, effectively from the nitrogen, but it doesn't come in one step. It has to fall off, and it has to go on there. The attack is from the nitrogen lone pair. Urethanes will also bond to amines, and so we can also integrate our surface with a polyurethane just by using an amine functionalized silane. As I mentioned, the choice of whether we want to use a silyl chloride or a silyl ether depends on whether we want to react it very strongly now, and it also depends on whether we can deal with the hydrochloric acid that is produced. So it's obviously not very good on surfaces that will be etched by the hydrochloric acid, and also we want to know how long it will last. And also we're interested in how well we can control the thickness of the coating. So if we have only one functional group on our silane, it can only form a monolayer, but it will typically form a bit less than a monolayer. If we have multiple functional groups, then it can form a solid on its own. That is obviously a danger, so it can be difficult to control, and it's a trade-off between the two. Water is required in the first step to activate the silyl ethers and turn them into the silicic acid analog, which then attacks the surface or is attacked by the surface. This is good and bad. It means that the control of water, or a little bit of water in our solution, is fine. We need a little bit of water, otherwise it won't react. Whereas the silyl chlorides are deactivated by reacting with water. They're more reactive than the silicic acid that is made. They still react in that case, but the silicic acid is not as reactive as the silyl chlorides. If we need that higher reactivity, then we need to keep the water away, and that requires more cleanliness in our process. If we need our chemicals to last a long time, which they would have to do if we need to transport them, if they are used in paints or adhesives, then we will obviously have to use something that is not as reactive, because it won't last. One of the massive advantages of silane chemistry is that it's comparatively easy to generate surfaces that have hydroxide groups at their terminus. If we have metals, we can just heat them up and then allow them to react with water a little bit. We could pickle them in acid or base. If we have polymers, we can react them with ultraviolet or plasma or something to generate hydroxide groups at the surface. That means that we can apply silane coupling agents to nearly anything. The major hole in that would be noble metals like gold and platinum that don't form an oxide layer very easily. And if they do, we can accidentally remove it. But the good thing about gold is that thiols work very well on gold. The intermediate things, like copper for example, are often a challenge because it is difficult to make a long-lasting coating.